So today we're going to discuss building a Butterworth bandpass filter using a method discussed by Dr. Broughton in his electromagnetic compatibility class and in a book titled RF Circuit Design by Chris Bowick. The idea is we want to use capacitors and inductors to build a passive filter to give us a frequency response we want, and using this method we can devise values for each of these components that will give us the frequency response that we want. And using this method gives us a frequency response that is precise, which is almost precisely what we want out of our filter. So a couple notes before we get started. We use this setup because the process we use, we need a ratio between this resistor here and this resistor, which we call RS for this one and RL for this one, which we'll get into in a moment. So how do we design this filter? Well, we start with a couple specifications. We need the dB per decade roll off from the pass band to the stop band, which will tell us the number of elements we need and the type of filter that we need. So the first step, after defining that, we then define a low frequency or low pass prototype, which defines a low pass filter with a cutoff frequency of 1 radian per second for the number of elements that we want. And then using those values, we can scale the frequency and the shape of the pass band to go from low pass to band pass to high pass to band stop. We can use techniques to scale the frequencies to get the frequency cutoff and to get the filter that we want here. So let's get started building this filter. So the filter that we wanted had a pass band from 885 megahertz to 2.145 gigahertz. And we were using a 50 ohm source to drive a 50 ohm load. We wanted 100 dB per decade of roll-off from the pass band to the stop band, which gives us an N of 5. For each N that we use, that's minus 20 dB per decade. So we used MATLAB to set up the problem and to crunch the numbers for us. This can be done by hand, but the computer does it just quicker. A little bit of background on this. The idea behind it is we want to build a bandpass filter with an insertion loss that looks like this in this area. And we can do that by using N, the ratio of RS to RL, and that will define a low pass filter that looks like this or like this, depending on the ratio that we have here. If our ratio is at the top, so if we're looking at this N equals 5 area, if we chose a ratio of RS over RL, we would use a topology that looks like this. If we chose an RL over RS, we would look down towards the bottom of our area, and this would be the circuit topology we would use. Since we have N equals 5, and we're in a unique position where RS is equal to RL, we don't quite have the ratio of 1 here. So we need to look a little bit earlier in the book and use this equation. A, which is the number that we're seeing in this area, is 2 times sine of all of this here for each integer k, from 1 to n. So in this case, n equals 5, so we need 2 for each a sub k. For each term, we'll do this from 1 until 5, plugging in 1 through 5 everywhere we see a k here. And that is all done in MATLAB, which we'll talk about in just a moment. So consulting back to this table, we're going to build a circuit that looks like this. We'll have a capacitor shorted to ground first, and then an inductor, and then a capacitor, an inductor, and so on and so forth until we reach our load. There'll be 5 elements in total. So looking at the MATLAB, the program we wrote to do this looks like this. We defined our frequencies, again at 2.145 gigahertz and 885 megahertz as our upper and lower cutoffs. We converted these to radians per second. As anything we're doing with circuit elements, we need radians per second. Here we find fractional bandwidth, which the derivation is in the book, but I won't discuss here. Define RS and RL and N here. In the MATLAB, we defined a matrix for each reactive element, which is the low-pass filter prototype that we see in this circuit here. The values that are in here go for each element in this circuit, and it's a low-pass filter with a cutoff frequency of 1 radian per second. So, as we start, we have reactive element LP. The first capacitor that we'd see would be the first spot in the matrix. The first inductor we see, or L2 as it's defined, is the second spot in the matrix, reactive element LP2, and so on and so forth. We have 5 total elements. Now, what makes this a bandpass filter is everywhere I see a capacitor here. If we go back to the LT spot, everywhere I see a capacitor, I sub out a capacitor and inductor in parallel going to ground. And everywhere I see an inductor, I use a series connection between the two elements, like so. So going back to the MATLAB, we defined up here at delta, which is our fractional bandwidth, using that value, the load resistance, and the prototype, either capacitance or inductance, we can find the values for each of these components defined here. So running the MATLAB code, run it, we open up the MATLAB, and here we see the reactive elements. So the first capacitor would be 618 millifarads. And the first inductor for the low-pass prototype would be 1.618 henries, and then so on and so forth for each subsequent component. These values, when connected to the topology that I've discussed here, would give a low-pass filter with a cutoff frequency of 1 radian per second. Now, using the equations here, we found effectively the components that we used to get a bandpass filter with the cutoff frequencies that we want. So looking at the components, it turned 5 of them into 10 output. We see that the first capacitor that we see would be 618 millifarads. Oh, my apologies, that's incorrect, that's the low pass. So the bandpass inductor and capacitor that we'd see is 8.546 nanohenries, and the first capacitor we'd see is 1.56 picofarads. And then the way that this code was written, all the parallel components were grouped together, and then all the series were put together. So each of these components here is the value of the inductor or capacitor that we put into the bandpass circuit that we want. So taking these values, I can then put them into LT Spice to simulate, which I've done here. As you can see, 1.5613 picofarads and 8.5463 nanohenries for the first element of our bandpass circuit. Now we have a discrete component bandpass filter that we could breadboard, test, put in the oscilloscope. But for the moment, we're going to use LT Spice to simulate, since it's an entry-level, easy-to-use simulation tool. I'm going to do an AC analysis from 600 megahertz to 3 gigahertz. And I want to measure the output voltage. And we can see a nice bandpass shape from about 2.1 gigahertz to about 888 or 885 megahertz. There is one note about these filters. They can get the way the method is. They do tend to get lossy as more elements come through. Hence this -6 dB from the source instead of 0 dB that would be coming through here. So we can see that if we assign a cursor, we can see that the spot where we hit, in this case, -6 is the passband here. We can see that at -9 dB is about is about 885 megahertz on the lower cutoff. And then going to the higher cutoff, the upper cutoff, we say that's about 2.15 gigahertz about. So this circuit, although it is lossy, will give us the frequency response we want. To correct just the lossy nature of the circuit, there could be a buffer put in, other measures. But this gives a good framework for values when designing microstrip filters in EDS or other simulation software for designing microstrip filters. Although this discrete component version, you can plug in the values into ADS and use that. So just to recap, this is a turn the crank sort of method on building a filter for use either in discrete components or microstrip filters.
Okay, so one possible tool that you can use for filter design is actually MATLAB. MATLAB has the RF toolbox. I used MATLAB online for mine, just using my NDSU credentials, and it worked really well. It was easy enough to use that toolbox and pretty straightforward actually to write your code and to use the functions provided. So I'll talk you through this RF filter function that was the main bulk of my code, and then I'll actually show you what I did in my code as well, and then those results. So the RF filter function, as you can see, pretty straightforward, creates an RF filter object. When you create it, you are able to pass a whole bunch of different properties to it. So for example, filter type, you can do Butterworth, Chebyshev, or inverse Chebyshev. You can do response type, so low pass, high pass, band stop. Implementation, you can either do the LCT, or the LCPi, which is what we used, or transfer function. Give it a filter order, give it your passband frequency, give it your stopband frequency, attenuation, source and load impedance, etc. So you don't need to pass all of these to it, especially if you're just using the default values. But we'll pop over to my code here, and you'll see that the first thing I did was make RF object, and to do that I used the RF filter function, set it up to be Bandpass Butterworth fifth order filter. Here's our passband frequency, our stopband frequency, and our implementation was LCPi. So as soon as we do that, just this first line of code here, that designs our whole filter. So then if we want to be able to dig into what exactly that filter was designed as, we can call the design data. So I just set up two variables here, L and C. L, I wanted the values of the inductors, and for C, I wanted the values of the capacitors. And if you head over to our results over here, you can see here are those inductor values, here are those capacitor values, and it's what we expected based off of the analytical data. The last thing I did was plot S21 versus frequency, which is another really straightforward thing to do within this RF toolbox, because they have a function called RF plot, where you just take the name of your filter and the frequencies that you want it plotted over. So I said from 0 to 3.5 gigahertz, and it actually plots that for you, does all of the formatting of it, which is really nice. That's all I had to do, was just put in this RF plot command. But as far as functionality beyond that, there's not really a lot of other straightforward things that function can plot. But if you're just looking for that S21 versus frequency, this was great. If you're just looking for being able to get the inductor and capacitor values, this is great. There are a few other things you can do, such as if you don't know what filter order you want, it can give you filter order, but it really does not have the same capabilities that we'll see from ADS. If you don't have ADS and you just have MATLAB at your disposal, this is definitely way easier than doing it analytically, especially if you know how to use these functions that I've shown here. So great for doing what I just showed, but if you want something with a little bit more power, then it would make more sense to use something like ADS, which we'll see in the next part of the video.
So today we'll be designing a 5th order Butterworth bandpass filter using ADS, and then comparing that filter with the filter that we calculated using the MATLAB calcs. So first off, just kind of a basic outline of what ADS is. So it is a software capable of doing anything required in electromagnetics, so designing microstrip filters, which is what we'll be doing today. Or if you look through the design guide here, there are amplifiers. You can also do mixers, oscillators, passive circuits. But today we'll be mostly focusing on the bandpass filter. So if you bring up the design guide here, we can see that we already put in the component. Now, there are two different types here. There is a single terminated filter, or there's a double terminated filter. So we are using the double. Now, you can adjust that when you go over here to Filter Assistant. So this is kind of where you do most of the design work. So you can see that on both sides of the filter, we have 50 ohms. So on the source side and the load side. You can also choose what your first element is. So we decided to choose parallel. Now the order, as you can tell, you can't really click into it and change it. The order is mostly that the software figures out. So it's a really intuitive software that way. So if we begin here, so when we go to response type, we of course want maximally flat since we're doing a Butterworth filter. And then down here, you can choose then all of your frequencies. Now we have chosen to do 500 megahertz up until 3 gigahertz. And we have our 2 cutoff regions set up as well. So fitting in all of these numbers, you get a design order of 5. Now, of course, if you wanted to adjust these to be more harsh, of course, your order is going to skyrocket. But with an order being 5, it made the calculations work well as the simulation. So once you do that, we can hit design, and then you get kind of this filter that now actually has stuff into it. So when you hit this button right here, this actually lets us go into that bandpass filter and kind of see what we're looking at. So what we have here is, as we stated before, our first portion of the filter is going to be parallel components. So we have the parallel inductor and the parallel capacitor, and then from there it alternates. So now after this first one, we'll have series inductor capacitor, and then it just kind of alternates back and forth. And then once again, to emphasize that these components just generate automatically. So that when you click into here, the inductance is set, the resistance of the inductor is already set, so everything's already ready to go. And then if you can see as well on the outsides here, we have our 2 ports. And then these are of course set up by, since it's terminated on both sides of the circuit versus just on one side. So the other thing that I added here now that actually isn't part of the circuit, but that we added for simulation's sake, is the S parameters. So with the S parameters, we have a start of 100 megahertz, and then it goes up to about 3.5 gigahertz, and we're taking a step of about 50 megahertz per step. Now, of course, we have it set on both sides, and we have it set at 50 ohms as well, just to be consistent. Now, there are two ways you can do the simulation. First way you can do the simulation is that if you go into the design guide, there's a simulation assistant, and once again, it does everything for you. But if you want to do it manually, just kind of make sure that you're doing everything right, you can do it that way. So if you hit simulate up here, you'll get a separate window that'll kind of detail what we're looking at here. So pull up this window, we can see that we have our two cutoffs right here, and we can see that the first cutoff is about 900 megahertz, whereas we spec'd a little under 900, so it's pretty close to it. And then we can see our other cutoff is 2.25, which is very close to our initial cutoff. Now, if we use those same steps, we can also realize our calculations from MATLAB. So once again, here's the same circuit that we saw before, but now when you actually go into the circuit, you'll notice that the values are just slightly different than what we saw with how ADS calculates it. So the important thing to touch on here is that the component values actually match the ones that ADS did. Now, they're not quite exact, but if we were to run the same simulation now, the parameters remain the same. So both are terminated by 50 ohms, and then they start with 100 megahertz and go up to 3.5 gigahertz. So now if we pull up both simulations at the same time, we can see that they're actually quite close in terms of the cutoffs. Now, the only thing that's different is going to be the second portion, so the second row, first column of the S parameters, where the ADS simulation is just slightly tighter than it is for the MATLAB calculations, which, if you think about it, it makes sense, since with the MATLAB calculations, there are things like human error, there are rounding, those sorts of things, versus when you do it through ADS, you're more certain that you're getting the best possible output for your filter. So now if we go back here, the next thing that we'll do is we're going to convert these portions of the circuit, so the parallel components and the series components, and we're going to change them into transmission lines so we can view them on a PCB layout. So now that we created our filter, now what we're going to try to do is we're going to try to convert those components that we calculated through ADS and through MATLAB, and we're going to convert them into microstrip lines that we can actually see and mill on a PCB. So the first thing we're going to do is go to the design guide, which I already have open. And then from here, so you hit this button right here. So what this guy does is we have kind of our components right there that we're looking at. So we go down here that says that we want our LCs to turn into microstrips. You can also do it through transmission lines as well. So we'll do our series components first. So we're going to convert them into just the single choice that's here, so into the microstrip line. So we're just going to use just the default microstrip substrate, and then from there we can just add our components here. And then you'll see that once you hit transform, you'll see that the width and length now are set up for the microstrip line. Now if we go back, we can do the same thing with our parallel components, except we're going to use this guy just because this one has a ground attached to it as well. So it saves us a step. So we can add all three of our parallel components and do the same thing. And so we can get out of here, and then now we have our substrate, which is set, which is what we have placed. Now this can of course be changed to your different materials that you're using, different heights. And then now we have set our microstrip lines to match whatever our LCs were. So next thing that we do is we go up to layout and we can generate. So now the nice thing with ADS is that it takes those microstrip lines and it takes those ports and it automatically converts them into what it would look like on a PCB. So we're just going to hit this one just in case anything gets out of whack. And then we can sync the entire design. So once we hit OK, we get our PCB layout right here. So I guess the big thing to see here is that if we pull up, so this is the MATLAB portion of it. So if we pull up the same thing, but with our ADS calculations, you'll see that the lines are mostly the same. So they look about the same. And the nice thing with ADS is that you don't even have to use just these basic microstrip lines that we designed here. There are a lot of ways you can incorporate some of the bow tie microstrip lines that we've seen around. You can also incorporate these bends as well. Lots of ways you can kind of solve this problem, but the big thing to know here is that when looking at between the different widths, so now let's go back into each respective schematic. We can look through and check each width, and you'll notice that they are almost identical. So that's the nice thing when working with, when kind of doing a low order filter, is that with low order filters, with order 5, you can clearly see that, okay, when you look at both widths and lengths, you'll see that they're mostly the same. Now, of course, the ADS ones are going to be just a little more accurate just because of human error when doing the calculations. But now if we were to go to a higher order and to be able to achieve this kind of accuracy, that's where doing calculations in MATLAB or even doing just hand calcs, that's where it becomes an issue. Versus with ADS, it's just a quick click of a button and then you can have your Gerber files and everything ready for your PCB.